Our goal here is to try to figure out how to measure the speed of galaxies moving toward or away from us. Whenever we want to measure speed in the sky, we end up using the Doppler shift. And I want to illustrate this for you one other way. You saw it in a previous video. But so I have here two little guys that I can drag around, a source and an observer. What I'm going to do is I'm going to start the source giving off some light. This could be any kind of wave, really. Light waves, sound waves, water waves. The Doppler effect works the same regardless. Now, if the observer, that's us, is moving towards the source, we're going to encounter these wave peaks more frequently than if we're just sitting still. So I'm going to start moving the observer, and as you look above at the observer, let me move. At the observer detected wave, you see that we've gotten it, pause, it was spread out more, and then it got closer together, spread out because I stopped moving for a second, closer together. So the wavelength got shorter, right? And that's what we'd call sort of like if it were light waves, a shorter wavelength means it's a blue shift. It gets more towards the blue part of the spectrum. So let me move the observer back here. Now, well, I guess I'll just move the observer away, and now you can see, since the observer is moving away, the wavelength is getting way longer, right? Because it's like moving along with the waves, right? So you see it stretch out like that. That would be a red shift, right? Because the wavelength is getting longer, the light is getting redder. Now that happens if the observer is moving, but it also happens if the source is moving, right? So if this object, say it's a distant galaxy, is moving away from us, then we'll see that the wave crests are going to be further and further apart, and the galaxy is going to be sort of red shifted. All right, so that's the Doppler effect. Again, it applies to any wave, but it also applies to light. Now, this isn't so noticeable that you would like look at a galaxy and you'd be like, wow, that galaxy looks really red, right? Because it's moving away from us. It's not quite that pronounced. Instead, what we do is we look at the spectrum of a galaxy. So just like stars have spectrum, galaxies have spectra as well, right? So this is roughly what the spectra of a galaxy would look like, and it's a little more complicated than that of a star. It has some absorption lines. Well, I guess first you see the full rainbow, red to blue, okay? And then you see there's absorption lines, little dark lines, and it also has some emission lines, the bright lines, because there's big clouds of gas inside the galaxy. And we can see some of those lines, typically the way we look at a spectrum by making it like a line graph like this. We can see some of the absorption lines, but also some of the emission lines. Now, what would happen is if the star is red shifted or blue shifted, and in general galaxies, they're red shifted, okay, because they're moving away from us, we see is that all these lines just shift towards the red part of the spectrum. Now, we know that these lines correspond to certain chemical elements, like, say, hydrogen. And hydrogen gas has these lines in very specific locations, like, for example, exactly right at 500 nanometers. Well, if we see it, when we look at a galaxy, we see those lines that we know are hydrogen, but they're moved over a little bit, and they're at 510 nanometers, then we're like, oh, wow, that wavelength has shifted. That's the red shift. So what's cool is not only do these emission and absorption lines act like a fingerprint telling us what kind of elements are there, they also kind of like they're markers that we can watch move to the right or the left, to get red shifted or blue shifted, to measure the speed. And the faster something's going, the more it shifts. So here's how this works in practice. This is kind of cool because we can see what astronomers really do, and we're going to use some of this data as we complete our assignment for this particular lesson. So here I'm going to show you the spectrum of a particular galaxy, and here's the full spectrum up here in the left corner, okay? And what we have here are just a couple zoomed in versions of just a couple parts of the spectrum. In fact, two prominent lines that we would expect to see. One are due to calcium, okay? These two little absorption lines are due to calcium, and this peak is due to hydrogen. Now what's also cool is it shows us with these little lines exactly where we would expect these absorption lines to be if the galaxy was not moving. And what's really cool about it is I can click on it. So if I click here, it tells me exactly what that wavelength is. So for calcium K here, it's 3933.5 angstroms. That's the exact wavelength, if I click on the line here, that I would expect it to be at if the galaxy were stationary. But it's not there. Instead, I go over to where the absorption line really is, and I click on it, click, and it's actually at 3966 angstroms. So it shifted over, like, how many angstroms is that? Like 20 to 30 angstroms. Okay, and so I can measure how much that shift is, and that'll tell me how fast the galaxy is moving away from us. Okay, I can do it here for hydrogen as well. I click on it where it's supposed to be in the lab. 6562 angstroms, that's what it would be if the galaxy were sitting still. Instead, it's actually at 6610, that's like 50 angstrom shift. Okay, now I should expect this roughly to be the same for both of these different kinds of elements if it's coming from the same galaxy, so it's moving at the same speed. I'd expect to see the shift be the same. So this is in general the process that astronomers would use to actually measure the speed of a galaxy.